Hi everyone, in this video we start section 16.5. I think sections 16.5 and 16.6 are the most difficult sections in all of Calc 3. And in particular, section 16.6 is the most difficult. So section 16.5 is really a warm-up for section 16.6. And in this first video, we're going to do a warm-up to a warm-up. So we eventually want to end up talking about parametric surfaces and the areas of those parametric surfaces, so how to find surface area of weird surfaces. And to start off, we're going to do what the easiest case in this video, which are surfaces that can be represented as functions of two variables. So how can we find a surface area of, let's say, something that looks like this using integration? So as I said, this is going to be the easiest case where we can represent this surface as a function of x and y. And so we just have some surface living above the xy plane. It could also be below the xy plane, but it's defined over some region in the xy plane, which we call D. Then how can we find the area of this surface? Well, let's derive the idea. So what we're going to do is think about breaking this surface into a bunch of different patches. And then in each patch, we're going to pick a point and find a tangent plane for that point over the patch. So imagine that we have a patch that looks something like this. This blue surface is a patch of the larger surface. We've picked a point and we draw a tangent plane at that point. Now, since this surface, this blue surface, is a function of two variables, I can figure out what these vectors are that are tangent to the surface going in an x and y direction. Because this vector, if it's going in a y direction, then the x component is 0. The y component I can just think of as the length of the patch. So let's call that length delta y. And then the z component, how is this vector changing in the z direction? Well, that's the partial derivative with respect to y. That's how the surface is changing with respect to y, times how far we're going in the y direction. Now, if I want to look at a vector in the tangent plane in the x direction, I get the same thing, just with x's. So the x component is just how far we're going in the x direction. Let's call that delta x. The y component is 0 because we're not going in the y direction at all. And then the z direction is the partial derivative of f with respect to x, which is also the partial derivative of z with respect to x, times how much we're going in the x direction. So now I have a tangent plane, or a small patch of a tangent plane above, or tangent to a small patch of my surface. I'm going to use this tangent plane to approximate the area of the surface. But this tangent plane is going to be a parallelogram, as long as these two vectors are not parallel, which they won't be because one's going in a y direction, one's going in an x direction. Then I can use them to find the area of this parallelogram, which is the tangent plane. And if you remember back to chapter 12, how do we find the area of a parallelogram? It's the magnitude of the cross product of two non-parallel vectors that are the sides of the parallelogram. So if I want to find the area of this parallelogram, I just cross these two vectors and then take the magnitude. Okay, so that's exactly what we're going to do. And I've got it all worked out here. So these outer lines are a magnitude. These inner lines, this is the determinant I use to compute my cross product. So then the first component, I get negative the partial derivative of f with respect to x times delta x delta y. The second component, I multiply by a negative, and I compute the partial derivative of f with respect to y, delta x delta y. And then the third component is just delta x delta y. So I'm taking the magnitude of this vector. This vector is what I get from the cross product. I'm going to factor this delta x delta y out, and I'm going to call that delta a. So instead of thinking of a change in x and a change in y, now I can think of a change in area. And I just take the magnitude of this vector left over, and I get the square root of this partial derivative of f with respect to x squared plus the partial derivative of f with respect to y squared plus 1. So this is the area of this small patch of tangent plane. Now, if I want a better approximation, I take smaller patches, and if I want to get the actual area, I take a limit of all of these patches as the size of the area goes to 0. So this delta A becomes dA, and I get the definition of surface area, which is an integral. So the area of a surface, where S can be represented by function of two variables, x and y, with continuous partial derivatives. So we assume that the first order partial derivatives of f are continuous, is this double integral. The integral over d, which remember d was the region in the xy plane where our surface was defined. The square root of the partial derivative of f with respect to x squared, so this is going to be some function of x and y, plus the partial derivative of f with respect to y squared, again some function of x and y, plus 1. You can also represent this as partial derivatives of z, just replacing f sub x with the partial derivative of z with respect to x squared plus the partial derivative of z with respect to y squared, because it's the same thing. Now this formula is similar to what you might have seen in Calc 2 if you saw it for the formula for arc length. Now there we were just finding arc length, so that's a one-dimensional curve. Here we're doing surfaces, which are two-dimensional. But if you wanted to find the length of a curve represented by f of x, where x went from a to b, the arc length was the integral from a to b of the square root of 1 plus f prime squared. So you can kind of see the similarity between arc length and surface area. Now it's just larger dimensions. So we have a double integral instead of a single integral, and we have more partial derivatives instead of just an ordinary derivative. Okay, let's look at an example. So find the area of the part of the surface z equals x squared plus 2y that lies above the triangular region with vertices 0, 0, 1, 0, and 1, 1. First thing I'm going to do is draw this region to come up with bounds of integration. So what's the region in the xy plane that I want to integrate over? And I'm not actually going to draw this surface. I'm just going to say, okay, the surface is above this triangle. It looks like something. Maybe I care, maybe I don't. I can use some software to graph it if I really care. And for this video, I didn't actually graph these surfaces. So if you're interested, we can talk about that in class, I guess. Okay. So to come up with bounds of integration for this triangle, we've done this a bunch of times now for double integrals. If I integrate with respect to y first, I'm going from 0 to x. So I get y's between 0 and x, and then x goes from 0 to 1. If I integrate with respect to x first, x goes from y to 1, and then y goes from 0 to 1. So you don't have to set it up two ways, but here are the two possible ways to set it up. Next, we want to calculate the partial derivatives of z. Z equals x squared plus 2y. So the partial derivative of z with respect to x is 2x. The partial derivative of z with respect to y is 2. Then I want to set up my integral and evaluate. Well, my integral, I already have my bounds from step 1. I'm actually going to integrate with respect to y first. You'll see y in a minute. So in y I'm going from 0 to x, and x I'm going from 0 to 1. And then I have the square root of 2x squared plus 2 squared plus 1. Well, 2x squared is 4x squared. 2 squared is 4. I add that to 1, I get 5. And now you can see why I'm integrating with respect to y first. If at this point I was integrating with respect to x first, there's not much I could do. Because to use a u substitution, I need an x sitting out front here. So I'm going to integrate with respect to y. I integrate, I just get a y here. I plug in my bounds. I get an x minus times the square root minus 0 times the square root. So now I just have an integral on x of x times the square root of 4x squared plus 5, which is exactly what I wanted to do the u substitution. So I let u equal 4x squared plus 5. Then du is 8x dx. So I'm just missing the 8, and I can think of this as u to the 1/2. So when I integrate that, I have the 1/8, which is left over, u to the 3/2, divided by 3/2, which is 2/3. I plug in my bounds. If I plug in 1, this gives me 9 to the 3/2. If I plug in 0, this gives me 5 to the 3/2. So I get 1/12 times 9 to the 3/2, which is 9 times the square root of 9, so 27, minus 5 to the 3/2, which is 5 times the square root of 5, and I get my answer. All right, let's take a look at another example. Find the area of the paraboloid 1 plus x squared plus y squared that lies above the unit disk. So for this example, I am going to draw the surface, just so you can kind of see, what it is and where I'm integrating over. So here's this paraboloid that's above the unit disk. So here's the unit disk in red. Using the same steps as the last example, I'm going to find bounds of integration using this region D. If I use Cartesian coordinates, these are all the points where x squared plus y squared is less than or equal to 1. So if I set up bounds, I'm going to have to use these circles to bound my variables. But it's going to be much easier if I use polar coordinates, right? We've seen this before. If I have a disk, I can use polar coordinates and just have r go from 0 to 1, and theta go from 0 to 2 pi. But this means that when I take these partial derivatives, which I need to do before I set up my integral, I need to convert these partial derivatives to polar coordinates as well. So I take a partial derivative of this function with respect to x, I get 2x. With respect to y, I get 2y. But then I need to convert both of those partial derivatives to polar coordinates. So 2x becomes 2r cosine theta, 2y becomes 2r sine theta. And now I'm ready to set up my integral. The surface area is the integral in theta from 0 to pi, the integral in r from 0 to 1, the square root of 2r cosine theta squared plus 2r sine theta squared plus 1. And then since we switched to polar, you've got to multiply by r. Don't forget to multiply by r. So dA becomes r dr d theta. From there, I'm just squaring things. So here I wrote the r out front now. So this is just 4r squared cosine squared plus 4r squared sine squared plus 1. I can think of factoring a 4r squared out of these two terms, and I'm just left with cosine squared plus sine squared, but cosine squared plus sine squared is 1. So this integral becomes the integral of, well, I'm integrating r times the square root of 4r squared plus 1. So this is almost identical to the last example. I can separate this integral. I couldn't separate the last one because there were variables in the bounds. So I'm going to go ahead and put this theta integral together. Use a u substitution for the r integral. U is 4r squared plus 1. Du is 8r dr. And then this integral evaluates to 2 pi. Here I have, if I multiply and divide by 8, I have u to the 1/2 du with a 1/8 out front. So there's by 1/8. Again, this is very similar to the last example. 2/3 times 4r squared plus 1 to the 3/2. If I plug in 1, that's going to give me 5 to the 3/2. If I plug in 0, that's just going to give me 1 to the 3/2. But 1 to the 3/2 is 1. If I multiply these three terms together, I get pi over 6. And so this is just pi over 6 times 5 root 5 minus 1. And that's the area of that paraboloid. So I'm going to stop here for now, and in the next video we'll start parameterizing surfaces.